Hello, welcome to the CCNA course brought to you by Eduonics. In this chapter we're going to be having a look at determining the technology and media access control methods for Ethernet networks, closely followed by identifying some basic switch concepts and the operation of Cisco switches. So, media access control methods. You may have heard the term CSMA-CD being brandished around in the past. That stands for Carrier Sense Multiple Access with Collision Detection, which is used in Ethernet networking. It's kind of self-explanatory if you break it down. Carrier Sense, in that it looks on the wire for any kind of collisions, or it looks for a connection. Multiple access, it can access both areas of the network, both ways. It's bidirectional. With collision detection, it can detect if something is collided and it can be retransmitted again. So it's basically a way to allow computers to transmit signal over network cabling while ensuring that only one computer transmits at a time. If two computers simultaneously place signals on the wire, then a collision can occur and the data might be corrupted unless a method is used to resolve the collision gracefully. Media access control method acts like traffic lights by permitting the smooth flow of traffic on a network, and they prevent or deal with collisions. Media access control methods are implemented at the data link layer on the OSI model, so we looked at that last time, and then after that you have CSMA-CA, Carrier Sense Multiple Access with Collision Avoidance. It avoids collisions, it does more checks to make sure that there's no signal on the wire before it sends anything, which is mainly used in Apple Talk networking. And then you have token passing, which is used in token ring and fiber distributed data interface networking, or FTDI. So FTDI provides 100 megabits optical standard for data transmission in local area networks that can extend up to about 200 kilometers, which is 120 miles. Although FTDI's logical topology is a ring-based token network, it didn't use the IEEE 802.5 token ring protocol as its basis. Instead, its protocol was delivered from the IEEE 802.4 token bus timed token protocol. In addition to covering large geographical areas, FTDI local area networks can support thousands of users. FTDIs offer both dual attached stations, which you may have seen shortened as a DAS, and counter-rotating token ring topology, and a single attached station, or a SAS, which is a token bus passing ring topology. And then we have demand priority, which uses 100 base VG networking, which isn't really used anymore. But really, what is a switch? Switches occupy the same place in a network as a hub, but unlike hubs, switches examine each packet and processes it accordingly, rather than just repeating the signal to all ports. Switches map the Ethernet addresses of nodes residing on each of the network segments, and then allow only the necessary traffic to pass through the switch. When a packet is received by the switch examines the destination and the source address and compares them to a table of network segments and addresses. If the segments are the same, then the packet is dropped or filtered, meaning if the destination address is the same as the originating address, then it will be dropped. If the segments are different, then the packet is forwarded to the proper segment. Additionally, switches prevent bad or misaligned packets from spreading by not forwarding them and dropping them. So filtering packets and regenerating forwarded packets enables switching technology to split a network into separate collision domains. The regeneration of packets allows for greater distance and more nodes to be used in the total network design, and dramatically lowers the overall collision rates. In switched networks, each segment is an independent collision domain. This also allows for what's called parallelism, meaning that up to one half of the computers connected to the switch can send data at the same time. In the shared network nodes, they would all reside in a single collision domain. They're quite easy to install. Most switches are self-learning, especially if you have a stack that are all the same make and model. They determine the Ethernet address in use with each network segment by building a table as packets are passing through the switch. it's essentially plug and play, and that element makes switches an attractive alternative to hubs. The switch can connect different network types such as Ethernet and fast Ethernet on the same kind of network, and many switches offer high-speed links like fast Ethernet and fiber as well to add much better bandwidth, so you can get a lot more traffic through the same network segment. A network that's composed of a number of switches linked together via these fast uplinks is called a collapsed backbone network. Dedicating ports on switches to individual nodes is another way of speeding access for critical computers. Servers and power users can take advantage of full segments for one node, so some networks connect to higher traffic nodes to dedicate switch ports, etc. Full duplex is another method to increase bandwidth to dedicate workstations or servers. To use full duplex, both network interface cards used in the server or workstation and the switch really must support full duplex. It effectively doubles the potential bandwidth of any particular link. And then we have the problem of network congestion. As more users are added to a shared network, or as applications requiring more data are added, performance will definitely deteriorate. You're not going to get a bubbling of an Ethernet cable like you see here, but you're going to see problems. It's all because users on a shared network are competitors for the Ethernet bus. A moderately loaded 10 meg Ethernet network is able to sustain a utilization of about 35% and throughput in the region of about 2.5 megabits per second after accounting for packet overhead, inter-packet gaps and collisions. A moderately loaded fast Ethernet or gigabit Ethernet shares about 25 megabits or 250 megabits of real data in the same circumstance. With shared and fast Ethernet, the likelihood of collisions increase as more nodes and or more traffic is added to the shared collision domain. Ethernet itself is a shared media, so there are rules for sending packets to avoid conflicts and protect data integrity. Nodes on an Ethernet network send packets when they determine the network isn't in use, and it's possible that two nodes at different locations could try and send data at the same time. When both PCs are transferring a packet to the network at the same time, a collision would be the result. Both packets are then retransmitted, adding to the problem, even though there is a particular back-off timeout that CCNA CD uses, and it's a random back-off timeout as well. So say if there was a standard timeout of a second, or maybe even 10 milliseconds, and each node retransmitted at 10 milliseconds, then there'd definitely be that kind of problem, whereby you get into an infinite loop of retransmitting data because the timeout's the same, the retransmit time's the same. There has to be like a random back-off timer for that to really work. So segmenting is where a network is divided into different pieces joined together logically with switches or routers. It reduces congestion in an overcrowded network by eliminating the shared collision domain, and collision rates are measured by the percentage of packets that are collisions. Some collisions are inevitable, with less than 10% common in well-running networks. So the kind of factors that would really affect network efficiency would be the amount of traffic, the number of nodes, the size of the packets, which is a big one, and the network diameter as well. How far does it spread out?